Welcome to EDU World Space.
All right, guys, we're doing chapter 9, problem 120. So the organic molecules shown here are derivatives of benzene, which is a six-member ring, and in which six membranes are fused, quote unquote, fused at the edges of the hexagons. Determine the empirical formula of benzene of these three compounds. So on the left you have benzene, and on the center left you have naphthalene. On center right you have anthracene, and on the far right you have tetracene. And if you count the number of, and when we do this skeletal structure for organic molecules, remember every point here that counts as one carbon, and I drew the hydrogens one. So we have, for benzene, our empirical formula is C6H6. X for our our molecular formula for benzene is C6H6. For naphthalene, it's C10H8. For anthracene, it's C14H10. And for tetracene, it's C18H12. So remember the difference between molecular formula and empirical formula. Empirical formula means that it will be a simplified formula. Like it just shows the proportion of the elements you have in your sample. So this is C6H6. So we can write that as CH. This is C10H8. So we can write that as C5H4. This is C14 in H10. This is going to be C7H5. And this one, C18H12, this can be C3H2. So those are going to be the empirical formulas of our samples. Now, for B, suppose you were given a sample of one of the compounds. Could combustion analysis be used to determine unambiguously which of the three it is? Well, yes. So let's say we're given one of these samples. We burn it in oxygen, and it gives us a certain amount of energy. The amount of energy that we have, the amount of energy given off is going to depend on which sample we have. The more CH bonds you have, basically the larger your organic structure is, the more energy you're going to produce. So tetracene is going to produce more energy than anthracene, which is going to produce more energy than naphthalene, which is going to produce more energy than benzene. So we can accurately determine which of these is our unknown sample based on how much energy is given off. Now, C, naphthalene. The active ingredient mothballs is white solid. Write a balanced equation for the combustion of naphthalene to CO2 and the CO2 gas S and water. S. So S. So we know what our S. So we know what our naphthalene structure is. And hold on. I'll just make a new page. So our naphthalene, that is going to be the C5. Sorry. I can choose the. I'll go with the molecular formula. C10H8 solid plus O2 gas yields CO2. Sorry, this is H2O gas. So let's balance this out. So we have 10 carbons on this side. We need to have 10 on this side. We have 8 hydrogens on this side. We have put a 4 in front of here. 4 times 2 is going to be 8. Now, how many oxygens we have on the right side? We have 2 times 10, so 20, plus 4, so that's 24. So that means we have 12 over here. So that's going to be our balanced equation. Using for the combustion of naphthalene. So now for part D, they want to use the Lewis structure for naphthalene and the average bond enthalpies found in table 8.3. Estimate the heat of combustion of naphthalene in kilojoules per mole. So remember, heat of combustion, we're going to use Hess's law. Delta H of reaction is equal to delta H of products minus delta H of reactants. So let's see how many bonds we have. First, we're going this. So let's look at the kind of bonds we have. So we're going to have CC. We're going to have C with a double bond. CH. O double bond to O. O. C double bond to O. And HO. So we're going to look at our table. So for CC, so for CH, it's 413 kilojoules per mole. H for CC is 348 kilojoules per mole. For C double bonded, it's 614 kilojoules per mole. For OO, it's 495 kilojoules per mole. And for 799, for C double bond to oxygen, 799 kilojoules per mole. And for OH, it's going to be 463 kilojoules per mole. Sorry, 463 kilojoules per mole. Now let's look at how many of each bond we have. So for our H2O, we have 2 of these. We have 2 OH bonds. For CO, in our carbon dioxide, we have 2 of these. For O2, we have 1 of these. And now for CH, since we have 8 hydrogens, that means we have 8 of those bonds. Then for CC, let's see, we have 1, 2, 3, 4, 5. Now for C single bonds, we have 1, 2, 3, 4, 5, 6. 6. So yes. So 1, 2, 3, 4, 5 of your double bond. Then we got 1, 2, 3, 4, 5, 6. All right, now we're going to use Hess's law. Delta H of products is equal delta H of reaction is equal to delta H of products minus delta H of reactants. So delta H, that's going to be 2 times that's 463. That's 4 times 2 times 463, because we do have to add the coefficient, plus 10 times 2 times 799 minus S, we have 12, and we have one OH bond, so we have 495 and let me see if I can pull this down, so I know I'm not going to have enough room for this. The 12 times 495 plus and we're looking at the number of bond, and we only have 1 mole, so we're going to be looking at 6 times 3, 4, 8 plus plus 5 times 614 plus 8 times 413. Now we're going to plug this in, put this in our calculator. So 4 times 2, that's 463, plus 10 times 2 times 799. So 12 times 4, minus 12 times 495 plus 6 times 348 plus 5 times 614 plus 8 times 413. And 12 times 495 plus 6 times plus 3 times 3, 83. So that means the delta H, so that's the delta H for this reaction. Hold on, I made a mistake. 463 plus 10 times 2 times 799 minus 12 times 495 plus 6 times 348 plus 5 times 614 plus 8 times 413. That's going to be equal to a delta H value of 5,282 kilojoules per mole. Else. Now, part E. Benzene, naphthalene, anthracene are colorless, but tetrazene is orange. What does this imply about the relative HOMO-LUMO energy gap in these molecules? So let's remember what our HOMO-LUMO energy gap is. So our so we have energy levels for specific electrons. Your HOMO is your highest occupied molecular orbital, and your LUMO, and let me just draw an electron here. Your LUMO is your lowest unoccupied molecular orbital. Your LUMO is higher in energy than your HOMO is. So remember when we talk about light, we're talking us an electron is as absorbs a certain frequency of light, and that frequency yes, and that will excite our electron to go from the HOMO to the LUMO. Us. So our electron will go from our HOMO, and it will go to our LUMO. And the difference in energy between your HOMO and LUMO, that's going to correspond to a specific wavelength of light that you're absorbing. Now, conversely, when your excited electron goes down to the HOMO, that's going to correspond to a specific wavelength of light that's being released. Like when we see that something is orange, that's not absorbing orange light. It's reflecting blue light. It's reflecting blue light, and that's what it's absorbing blue light and it's reflecting orange light, and that's the light that we see in our eye. Like I said before, the difference in energy between the HOMO-LUMO gap, that determines what color you're going to see. Now, when we talk about white light is the combination of all light in the visible spectrum. So if we see something that looks white, that means that it's not absorbing any light, and it's reflecting all the wavelengths of visible light right back at us. Yes. So if no light is able to be absorbed, that means the difference between our HOMO and LUMO is so great that you can't excite your electron using visible light. So that means that, for example, our benzene is going to have a greater HOMO-LUMO gap than our tetrazene does. So, and we can see that as we go from benzene, naphthalene, anthracene to tetrazene, eventually we are going from a white solid to a colored solid. And so that means that as we are adding more and more rings to our organic molecules, then that means you're what's the word I'm looking for? You're shortening the distance between your HOMO and your LUMO. Oh, and so that means that for tetrazene, its HOMO-LUMO gap is short enough that our electrons can be excited from our HOMO to our LUMO, and you can make the transition from the LUMO to the HOMO, and that energy transition causes the orange light that we're seeing. So that means that like I said, that means that as you were adding more rings to your organic molecules, then you're gradually closing the gap between your HOMO and your LUMO levels. So that transition from HOMO to LUMO, that becomes a lot more energetically favorable. And that's it for this question.